Hello everybody, how are you today? So we're going to continue with the autocorrelation function for MA2 models. So we have seen earlier where for MA models, so if you're using using the ACF to identify the order of moving average with order of Q, then you expect to see a cutoff after Q lags, and then the PACF will be tails off gradually. So we have discussed about the MA1. So this is the MA1 simulated model, and we found that there's only one significant spike in the ACF plot. Okay? Of course, this is the variance. Okay? So this is the leg 1 autocorrelation function. So for MA2 models, this is our MA2 models. So we found that the the ACF actually have two significant spikes. Okay, so the rest of it actually fall within the 95% boundaries. Okay, so we already showed that the MA1 actually will be 0 any lags more than 1. Okay, so all the ACF after leg 1 after leg 1, which is 2, 3, 4 until let's say 20, are all within the 95% boundary. So in this session, we're going to look at the MA2 models. Okay, why there's only two significant spikes. Theoretically, yes. Okay, so we can show this theoretically. So we just use the model specification. So you have a MA2 model, which you can written in this particular form. Okay, so you have two legs of the residual or the noise. Okay, so you have a ZT. So you have first term of leg of noise, and then the second term's leg 2 t minus 2. Okay, so again the ZT overall, or the ZT minus 1, ZT minus 2 are all white noise with the mean 0 and variance which is a constant. Okay, so if you like to determine the covariance of the xt and the lag of k or lag of tau, so you can actually define your covariance between the xt and xt plus tau. Okay, of course you can use xt minus tau where because you know that covariance is an even function, so the covariance of lag minus tau and plus tau actually are the same. Okay, so by doing so, you can actually expand this, the covariance between. So xt, you can just rewrite the equation in this particular form. Then you have a zt plus theta 1 plus theta 2. Then if you have t plus tau, then you have zt plus tau theta 1. So t plus tau minus 1. Okay, t plus tau minus 1. Then you have a theta 2 z t plus tau minus 2. So this is the covariance we like to develop. So we know that the covariance, in short, the covariance basically in the exponential form, in the expected value representation, you're going to have xy minus the individual x, the individual expected value of y. Okay, so you're going to do the same thing, x representing this term, x minus tau representing the y. So you have a linear combination of all the expected value. Okay, so you can form all this. So you're going to have many terms. So basically you have 9 terms overall. So we can just write down one by one. So first is zt and zt plus tau. Okay, so the second terms, you have e of zt theta 1 zt plus tau minus 1. Then you have Actually, I should use a bracket. Actually, it's the same this one. So if you use bracket, then it should remain as bracket. So some notation is it's no harm written in the bracket in this form. So then the last one will be the ZT, the third term, not the last one. Data 2. Okay. So then the next term and the rest of it. Okay, so you have another 3 terms. Data 1, so we can just take out the data 1 first. Take out the data 1, straightforward. So you have a data 1 E of ZT minus 1 and ZT plus tau. So next one you have data 1 and data 1 square, okay? Data 1, data 1, so you have data 1 square, so you have E of ZT minus 1 and T plus tau minus 1. So then last one is data 1, data 2, the sixth term, ZT minus 1 and ZT minus plus tau minus 2. Okay. So the last pair, 3 pairs is this, this, and this. Okay. So you have plus data 2, ZT minus 2 and ZT plus tau. T minus 2, ZT plus tau. So then you have data 2, data 1, data 1, data 2, ZT minus 2 and ZT plus tau minus 1. So the last term will be data 2 square ZT minus 2 T plus tau minus 2. Okay. So this will be the overall general terms of covariance between T and tau. So basically this is covariance of, this is actually the covariance of tau. Covariance of tau. So now we just put a specific value for tau, then we can actually generate the covariance function and then correlation coefficient for the different tau involved. Okay. Okay, now for specific tau equivalent to 0, okay, so this is how we find out the value. So if tau is 0, according to this, xt and xt. Okay, if tau is 0, isn't it? This is 0. So this term is 0, so you have zt, zt. So you have e of zt squared, e of zt squared, or zt and zt, let's say. Okay. So you just check the terms where, yeah, we know that if, so we also know that if all the covariance, okay, covariance of two different, knowing that the covariance of zt or zs and zt or zrs, not to be confused, zr and zs will become 0 if r is not equivalent to s, right? Because the z value is a random process with mean 0 and variance sigma squared. Okay, so therefore there will be no correlation between zt and zr and zs if they have the same length. So if t0 and t0, for this case, who else? This one is t plus t minus 1. So this one will be 0 straightforward. T and t minus 2 is 0. This is t minus 1 and t 0. T minus 1 and t minus 1. Okay, so data 1 square is one of the term, plus data 1 square e of zt minus 1 zt minus 1. Okay, then you have t minus 1, t minus 2, t minus 2, t minus 2, and t minus 1. So this one also square e of zt minus 2 zt. So this should be the multiplication. So this shouldn't have any comma anymore. So this is zt. So this shouldn't have any comma here. Sorry about this. Just cancel this comma. Comma when it involves with the covariance. This is an expected value. Sorry about this. So this one shouldn't have a comma. You just multiply the series. Covariance, yes. So here there's no comma. So this is zt minus 2. Okay. So at the end, we know that this is the variance of zt. So we know that the variance of zt is what? Variance of zt is sigma squared. Okay. So why? Because the variance of, sorry, we're talking about variance of zt, then this is actually e of zt squared minus e of zt, the whole thing squared, isn't it? So e of zt is actually 0. Okay, so therefore the variance of zt actually is the expected value of zt squared. Okay, so this one is actually the variance. This one is the variance as well. This one is the variance for zt. Okay, so this one basically is a covariance of xt. Okay, so there are two series here, xt and zt. Xt and zt. So you can rewrite this in the form of sigma squared 1 plus theta 1 squared plus theta 2 squared sigma squared. Okay, so this is the first, or the covariance of xt. Okay? So we do the same thing when you substitute tau equal to 1. Okay. Back to this equation, any terms where the zt and zt are the same, then you have a non-zero value. Okay, non-zero value. So look at covariance of xt and xt plus tau, isn't it? So now tau is 1. Okay. So this one you have 0, 0. So this is t and t. So this will be the first one. Okay. So theta 1 is the non-zero terms. Theta 1 e of zt and zt. Then you have t minus 1, you have t minus 1 plus 1, isn't it? So this one is non-zero. So theta 1, theta 2 plus theta 1, theta 2 expected value of z t minus 1. So z t minus 1. Okay, so this is the value. So the rest of it are basically all 0. This is plus 1, so the lack of 2. So this will be the only terms. So you have theta 1 sigma squared plus theta 1 theta 2 sigma squared. So you can also rewrite these terms as 1 plus theta 2 theta 1 sigma squared. Okay. I think we should put the theta 1 in front. Okay, it's a bit weird. So this one you can write equivalent to theta 1 sigma squared. Okay. Okay, how about tau equal to 2? 2 step ahead. So you have a covariance xt plus 2, isn't it? So according to this value, the only term which is non-zero will be theta 2. So this is t minus 2, this is t plus 2, sorry. So theta 2 so this t plus 2 t minus 2. Okay, so this is the only terms. Okay, so you can take out the data 2. So why this is not taken out? This one should be taken out. Okay, this one should be taken out. So you have data 2 times e power e zt times zt. Okay, so you have this term data 2 e of zt and zt. So this will be only terms. You have data 2 sigma square. So now if you substitute tau equal to 3, 4, 5 and so on, then you find, so this one should be taken out, okay? This one, because it's a linear, the constant, you can take this out. Then why am I not taking out this? This one, these are all taken out, is it? Because it's a constant, okay? The expected value. So this one you take out, this one you take out. Okay, then you obtain this. So if we use t equal to 3, obviously the expected value of all these value will be 0, okay? Because there's no single zt have the same legs, okay? So therefore all will be 0. So tau equal to 4, 5, 6, 7, 8, all will be 0, okay? Similar to MA1. So in this way we can form the covariance function, okay? Covariance of, let's say, tau, which is the covariance of xt and xt plus tau, let's say, or xt minus tau, okay? It's the same. So you're going to have 4 types of value. So for tau equal to 0, first you have 1 plus theta 1 square plus theta 2 square. The whole thing sigma square, is it? So this is when tau is 0. Okay, this one. When tau is 1, this is a value. When tau is 2, this is a value. When tau is 2, you have theta 1, 1 plus theta 2 sigma square. This is tau is 1. Then you have theta 2 sigma square. This is tau is 3. Then all the rest will be 0 if tau is larger than 3. Or tau is start from 4, 5, 6, 7 and so on. Okay? So if you have a covariance function, we can actually determine the ACF. Okay? The ACF, which is the rho of, or actually R, okay? For H or tau. So this is basically equivalent to the gamma of tau over the gamma of 0. Okay? So just substitute this value over this value over this value. So this, therefore the first term for ACF is always 1. Yeah? So this is tau equal to 0. So when tau is 1, that means this value over this value. So you cancel the sigma square, you have this over this. Okay? So you're going to end up with theta 1, 1 plus theta 2 over plus theta 1 square plus theta 2 square. This is 1. So tau equal to, sorry, this is 2. This is 2. So for ACF leg 2, this over this. Okay? So then you have theta 2 over 1 plus theta 1 square, theta 2 square. Okay, so this is tau is 2. And the rest of it are all 0, and this is larger than 2. This is larger than 2, sorry. Or you can equivalent to 2, right? Larger than 2. Okay, so this will be our ACF for MA2. Okay, so obviously you can see for leg 1 is non-zero, for leg 2 is non-zero. So you can easily, or you can just substitute the non-zero value for, let's say, e.g. we put the 0.3, theta 2 is 0.5, then definitely these two legs are non-zero. Okay? So therefore you're expecting to plot ACF with a form of, this is the leg, this is your ACF. So this is leg 0, so you always get 1. So you have leg 1, leg 2, 3, 4, 5, and so on and so forth. So this will be two non-zero value in your ACF. Okay, so therefore you only see two significant spikes. So theoretically, this one should be all zero. Okay? But since if you're doing a simulation, you will get something which is non-zero. They still have a very weak serial correlation with like 3, 4, 5, and so on. Okay? But theoretically, this is should be all zero exactly. Okay? So you have seen two non-zero significant spike. Statistically, a non-zero. Okay, that's what we have proven here. Okay? This is non-zero. This is non-zero. So you only see two significant spike in the MA2 mode. Okay, so you can extend this to MA3, 4, 5, and so on. But the ACF equation or function will become more and more functions involved. Okay, more legs. So if MA3 you're expecting to have three non-zero terms. Okay, three non-zero terms. Okay, guys. So this is more or less about the ACF. We use the If you use it to identify the moving average model with leg Q, you should be able to see the numbers of significant spike according to the order, let's say Q. If Q is 1, you have 1 spike. Q is 2, you have 2 spikes. Okay, guys? So thank you very much. I'll see you guys in the next session.